All right, I'm going to check on piazza. What's happening there? Equation sheet number 2. Momenta means momenta. That's a typo. I will fix it. Plural. I think that was fixed. I'm not sure. I need to take a look at this. Lecture problem with distance and friction. No, it should be squared. The equation has squares. I have to check it. Did I do it? Squares. Homework 2, part 2, question 3. Homework 2, part 2, question 3. Homework 2, part 2. Homework 2, part 2, question 3. 1, 2, 3. Wooden block is at rest. On a rough horizontal surface, when a bullet is fired horizontally, after the impact, the combination slides. All right. So this problem is physically identical to a problem with a bullet hitting a ballistic pendulum. It also has two parts. And for each part, we have to apply its own law. First, we have a collision, law of conservation of linear momentum. Second, we have moving. Well, in this case, it was a change in height. In this problem, the bullet flies, hits the box, collision, the law of conservation of linear momentum, and then the second part starts, the motion, sliding. And the law of conservation of mechanical energy worked in a class for the pendulum, but here I would use work kinetic energy theorem because there is friction. That means now you have to solve two problems in one. For the collision, the mass of the bullet times speed of the bullet before the collision plus the box was not moving will be equal to, right after the collision, total mass times the speed of the box with the bullet. But this is the speed that is the final speed for this process. And at the same time, this is the initial speed for this process. It's the same speed, but it has different meanings. Now the box starts sliding. So for the sliding, it starts sliding, having this initial speed. Eventually, it stops. This is the distance traveled. In the middle, or somewhere between these points, we've got normal force acting on it, gravity, friction. Friction does work. So change in the kinetic energy has to be equal to work done by friction. And that kinetic energy, where the initial kinetic energy here, mv initial squared over 2 is actually mv box with the bullet squared over 2. And this should be the total mass, total, which doesn't matter, it's getting canceled. So the reasoning leads us kind of from left to right. But now we can start plugging in numbers, solving, and the solving goes from right to left. That's how it's supposed to be done. First, we need to apply log conservation of the linear momentum, then work in the theorem, and solve them backwards. Pretty good, only one typo. I thought that should have been the case. All right, office hours, slide 2. All right, let's see. Calculate force. Here we need to multiply mass and acceleration. Let's do it one more time. That's the force of tension. Normal and gravity cancel each other out. So all we have is this net force is equal to tension equals mass times acceleration. For the motion with constant speed, uniform circular motion, that's going to be equal to centripetal acceleration speed squared over the radius. And speed and the angular velocity omega are related. So we can continue calculation. Omega squared r squared over r, omega squared times r. Now, omega was equal to 3 revolutions in 2 seconds. So 3 times 2 pi radians over 2 seconds. This will give us radians per second. And the radius is equal to 50 centimeters. So what do we have? And the mass, half a kilogram? Yes, half a kilogram. So 0.5 times I don't know how was so it's 3 pi squared times 0.5 newtons. Mass, and what was it? I'm not sure. Ah, 0.5 is point is missing for the mass, 0.5. Or maybe this dot just wasn't converted. But the rest seems correct. We can check calculation. So should be 0.5. Should be 0.5 times 3 times pi squared times 0.5 from the radius equals, where's my calculator? My calculator, 0.5 times, actually 0.5 again, the radius equals 0.25 times 9 times pi squared. Where's pi? I don't know, I get 22. I believe in a slide the dot disappeared. Sometimes it happens. Block slides. Why do we use the equation work of gravity mgh? It does not matter what is happening and with what work done by gravity is always equal to mg y initial minus mg y final. But it also can be found using the equation for the work done by a constant force. Work is always equal equation loop problem. Did the work? Okay, but on the slide, the answer is potential energy. So maybe I use the different reference point. Let's see. So here in this slide, the reference point is at the bottom. So mgy initial is equal to mgy final plus kinetic. What is that? Is I don't know. From the bottom, y initial. This is 0. R, and right here it travels to the right, and mgy initial plus 0 should be equal to mg2r plus mv squared over 2. So gy initial equals 2gr plus v squared over 2, or y initial equals 2r plus v squared over 2g. Now, when the normal, okay, here at the top we've got force of gravity and the normal force acting down, centripetal acceleration points down. So the Newton's second law says and the critical speed means the normal force becomes 0. That tells us mg equals v squared over r. V squared over r, m cancels. So gr equals v squared, and 2r plus 1/2 over gr. I should use the same r's, I guess. R. So 2r plus r over 2, which is 4r over 2 plus r over 2, 5r over 2. 5r over 2. That looks like a correct result. So the typos. Something is happening in my brain. The finding a mistake actually is harder than doing it right in the first place. So if anybody can check it, please check. The right answer is 5r over 2. Unread. Homework 2, part 3, problem 2, homework. All right, I need to close this. I have to go to part 3. Part 3, problem 2. And problem 2 is about this. So I believe that some people don't read instructions because instructions provide important information. So for problem number 2, we need to calculate how much is the initial location, which is not shown higher than the top of the loop, all right? So this is not what we're looking for. This is just a part of the picture. And all right. Oops, what happened? Okay. So I've never been on a roller coaster and I will never be. What I know is it starts here from rest. So this is the initial situation. The initial speed is 0 and then it slides down. And here it travels through. That's the instantaneous velocity. And now this is identical to the problem just solved for the loop. What we're looking for is not the height from the ground. It is how much higher you start than the top of the loop. This is what you need to calculate. So in this situation, you have to set the origin at this level. But you know that when the roller coaster travels through the top, it is a part of a circle with a given radius, right? Yes. So downward acceleration, that's the centripetal acceleration. And it has to be equal to speed squared over r. And in this situation, it is given to you. It's not critical. The speed is not critical there. The normal force is not 0 there. That is why you cannot apply the expression for the critical speed, because the speed here is greater than critical. You actually have to calculate speed because you know your acceleration here is supposed to be equal to 1.5 times g. The critical speed means your acceleration would be equal to 1 times g. That's the difference. Where is piazza? That's not piazza. This is piazza. Because in this case, the speed at the top is not critical, but higher. Just one typo. All right, what's next? Forces. That's a cool problem. On a stick from wall. What's the question? It's not always the case. Maybe in this problem it is a case. But in general, this may not be the case. In general, the force at the hinge might point in any direction. It depends on the problem. No typos. All right, and we are done. Done.